In this video, I'm going to show you how to perform an enzyme kinetic analysis based on the Lineweaver-Burk model. And therefore, we look at that data set here, which comes from an enzyme kinetic assay where galactosidase cleaves the substrate ONPG into galactose and orthonitrophenol, which is a yellow substance. So with the progression of the enzyme cleavage, our solution becomes more and more yellow. And we can measure that, for instance, using a photometer. And from the raw data, you calculate the velocities of the reaction in, for instance, millimolar per minute. And that's what I already did before. And when you plot that data here, you see that looks reasonably hyperbolic. And some of you might know that that simple kind of data is often described by a Michaelis-Menten kinetic model, which is in fact a hyperbolic that has two parameters: the maximum velocity, so the value that curve approaches for infinite concentrations, we call it Vmax, and also the Michaelis-Menten constant that corresponds to, let's say, the values, the concentration where 50% of that reaction rate is reached. So we start at 0, 0, hyperbolic, right? And let's say that approaches more or less 100. So assume that Vmax is 100. Then we would have, like, whatever, at 50 there is about 2.5 millimolar is the Michaelis-Menten constant. Yeah. Good, but we will see the exact value when we do the analysis. Typically, these kind of data are fitted using a nonlinear regression. If you have dedicated software at hand that can do that, but you can also do it in Excel, and I will maybe later show that how to do that in a dedicated video. But here we will apply a transformation to linearize that data, which is based on the Lineweaver-Burk analysis, and we will apply linear regression afterwards. And especially we'll apply a weighted linear regression, and I will show you how to do that in a few seconds. To be able to analyze that in Lineweaver-Burk way, let's say, we transform that data here by just taking the inverse of that vector element-wise. So here, I did that here below. And you calculate 1 over the entries of that vector element-wise, and the same you also do for the velocity vector. 1 over that velocity vector element-wise, and there you go with that data here. And I've plotted that data here and that chart, and you see that this data here is reasonably linear. And you might be motivated to fit that using a conventional linear regression. And many people do that, and it might work in practice to some extent, but it sometimes fails, and you get some negative Km or even negative Vmax, which is biophysically meaningless, right? That fact was already discussed in one of the papers of Lineweaver-Burk, and they suggested using a weighted linear regression, and they weighted by 1 over the velocity rate to the power of 4. That was their suggestion, and they published a paper on that with a statistician and worked out everything why that is a good choice. Anyway, we will discuss first what is linear regression in matrix terms, and I will remove that W here, ignore it for the moment. So that here is the matrix equation for linear regression. Conventional linear regression, no weights at all. And the X is the Jacobian matrix, which has 1s in the first column and the X values in the second column. Yeah, and you might know that here as the so-called pseudo-inverse. Yeah, and you multiply that pseudo-inverse times the Y values, the Y vector, and then you finally end up with these parameter estimates. Yeah, and we call them B hat. These do not directly correspond to Km and Vmax, but I will show you how to transform that to Vmax and Km, which is very simple. Okay, so let's apply maybe that simple linear regression first, and then we will compare the results to the weighted linear regression. We transpose the output of the line_est function. So line_est is actually internally performs that kind of analysis in matrix terms, and line_est is known y's, known x's, and be estimated normally, and so on. So here we go. Good. So these are the parameters. That is the slope. Sorry, no, the intercept. That is the intercept. That is the slope. Yeah. That is the way the line_est outputs these parameters. And we can calculate the Vmax value by simply inverting the intercept, of course, by inverting the intercept. So there we go. That is the Vmax. So that is Vmax. And we can calculate Km by intercept divided by slope. No, the other way around, of course. L2 divided by L3. There we go. So that is Km. Okay, let's make these guys bold here. Okay, so these are the values Vmax and Km. But as I said, now let's compare that to the weighted linear regression. And how do we weight? As Lineweaver-Burk suggested, we can weight by 1 over the y values to the power of 4, right? We'll do that element-wise again. So here, that vector, so that is 1 over that value to the power of 4. And then we apply a weighted linear regression. And for that, I will input the W again, which is the weighting matrix. And the weighting matrix is a diagonal matrix that has those elements on its diagonal, right? Before, that used to be a unity matrix, so we could more or less ignore it, let's say. Or at least that times the unity matrix is still that thing here. But now we apply those values, which are not ones, in that matrix, and we will have, yeah, that's that complex looking formula in order to calculate this vector b again. And here I already calculated Vmax, 1 over f2, f3 divided by f2. Yeah, so that's these two guys actually reversed compared to the conventional linear regression. Okay, so now here we use the discrete y values for the weighting. I think probably it might be a good idea to apply an iteratively reweighted least square scheme here. So we do not weight by the discrete y measurement values, or not directly measured, but calculated from the measured values. But we might apply an weighting that is related to the theoretical fit curve, so y hat. And what we can do, instead of using those guys, we simply, and I drag that here to the right, we apply that y hat for the weighting. So, and that only works if we have the iteratively calculations activated in Excel. Otherwise, here we would run into problems. This guy here depends on those two guys, right? So you see here we have this guy here in that formula. But actually that formula also indirectly applies, because that is related to that, applies these values. So there's a circular reference problem that Excel is warning us about. I can induce that when I disable those iterative calculations. So it says Microsoft Excel cannot calculate a formula. There's a circular reference, right? So you see there's a problem, right? And now let's enable this again. Enable iterative calculation. That is important, otherwise it doesn't work. And right, here we go. These are our two guys, right? And from then we can calculate Vmax and Km. So here again, we've weighted with a theoretical model, so the linear curve in between. And in principle, that is an iterative procedure. So we estimate a line in the first cycle through the data points, use that line to calculate weights here, then do that formula here, basically that. So estimate new parameters, use these parameters again to calculate that line. From that again we calculate the weights, and so on and so on. And that is what I tried to point out here in this formula. So B hat I, which is at the ith cycle. We use the theoretical data, so x times b at cycle I minus 1, to calculate the weights, which corresponds to that part here, 1 over that part to the power of 4, that which corresponds to those weights, and also here. And again we cycle all the way through. That is this iteratively reweighted least square thing. The drawback of that is actually that you still need, or similar to nonlinear regression, you need initial guess values, and that makes this formula a little bit more complicated than the conventional linear regression part here, with either constant weight or unity weights. Yeah? Otherwise, it's probably the better method to do the Lineweaver-Burk analysis. Of course, if you have multiple replicates, for instance, so you might calculate their averages and use these averages here as weights, and that might also work pretty good. And now, instead of 2.9, we got 2.7 for that weighted linear regression. And Vmax of 105.78. These are quite close. But as I said, it doesn't always work that conventional way, so it's maybe more accurate to do it that way, as we did it right at the end. And yeah, let's draw that line probably just to get an idea how it looks like. X values and y hat, that is the y hat of that final cycle, which is good. That's exactly what we want, and there we go. Okay, so basically you can simulate conventional regression here as well. So just simply put a 0 there, and there you go. Then you have the conventional regression, right? But we stick with 4 to have our weighted linear regression. But what I wanted to point out, maybe you've realized that although that conventional regression looks a little bit better because that data point is more close to the theoretical curve, or the other way, the theoretical curve approaches that data point a little bit better, the weighted form of that regression, let's say, removes the weight of that data point, because that is supposed to be less accurate after the transformation, because after transformation the scatter here tends to increase for increasing x values, right? But you cannot, but it's just difficult to see here, but you can already guess that from that data. Yeah. And to give that data point a little bit less weight, we apply that 1 over y to the power of 4 weighting. Okay, thanks.